Swayam Prabha. Digital India. Educated India.
Positive definiteness done, radial unboundedness done, easier tests done. Now we go to decrescence. Yeah, this is the third property. Okay, a function is said to be decrescent. Again, you see this local domain and all that, mapping to real numbers. Yeah, this cannot change because the same function is what is being used for analysis of this stability analysis of the system. So the domain, range, and image sets cannot change. Okay. So for decrescence you require that the function is 0 at 0, again cannot change because no Lyapunov function is allowed to be non-zero at the equilibrium, and we assume 0 to be the equilibrium. Okay. For all time, and there exists a class K function such that in absolute value this function V is dominated by the class K function. Okay, just digest it, that we have, it is mentioned in a slightly different way. You have put in the absolute value here, yeah, we are not, which means we are not restricting somehow the V from being negative. Okay, earlier definitions like class K and so on more or less guarantee V is non-negative, because it is 0 at 0 and then it is dominating a class K function which is strictly increasing, it means V can never be negative. Here somehow that is being allowed, yeah. So again of course it is for all time in R plus and X in BR, these things are standard. So the picture looks something like this. When you draw the phi norm of X, yeah, you also draw the negative of that and your V has to lie between that. This is what the picture looks like, because I mean I am just translating this into this image right here. Okay, all right. Now if we go back and look at, which we did not use, at class L function, okay, at a class L function, and do you think we can actually instead of using a class K function there, okay, that is phi is class K, do you think we can characterize this decrescence in terms of class L functions? Anyway, this is a question I want you to think about, so I will put it as an exercise. Can you characterize decrescence using class L functions? Yeah, because there it is like, because this is also somehow doing a upper bounding, right, instead of a lower bounding. It seems like it is doing a upper bounding instead of a lower bounding, right. So the question is, can you use class L functions in some sense? Okay, can you use class L functions to characterize decrescence functions? Okay, this is a, I want you to think about it. Yeah, all right. Okay, let's look at some of the functions we have already considered. Yeah, this was one of the functions we considered. Yeah, this is a function which is positive definite, right, because it dominates this, which is a class K function, right, so but does this, is this a decrescent function? Is this a decrescent function? Can this be dominated by a class K function? So the flip question, right? Until now for positive definiteness you wanted this to be greater than some class k function, which it is, because if t is non-negative, then if t is non-negative, then this is greater than equal to norm x square divided by 1 plus norm x square, right, and that is a class k function. So great, it is positive definite, right, or you can even verify positive definiteness via the easier test, the easy test, right, same deal, no difference. Okay. Now for decrescence what do we need? We need it to have some upper bound with some class k function. Okay. So usually it is not very easy to claim something like this, okay, in the sense you would be very hard pressed to prove that there does not exist or there exists a class k function, okay, which dominates this function. Not easy, because you have to test every possible class k function, right. Matlab, this is only one possible class k function with which we prove positive definiteness, okay, and so I am asking a simple question, does there exist some R such that this happens, okay. It is rather obvious that this does not happen for any R, right, because if you give me any value of R, I can push up time so that this condition is violated, yeah, because these conditions have to hold for all time, right, you can see that this condition has to hold for all time, right. So I can always push up time such that for this particular choice of class k function things go wrong, okay. But now how can you guarantee that for every possible choice of class k function things will go wrong? I have just shown that for one choice of class k function things do not work out, but can I just categorize this as being not decrescent? Or how would you claim that this is not decrescent? How would you claim that this is not a decrescent function? I have shown that for one choice of phi x, this kind of upper bounding will not work. Can you say the same for every possible choice of phi x? Yes, no. Think about it. So will this fail? Will this fail for this example? For arbitrary phi x now, not this specific choice, because I can't say that it did not work for one choice I made, so it is not decrescent. No, that is not true. There cannot, the negative of this is that there does not exist any phi x, okay, does not exist any phi x. Can you claim that this is indeed the case? I am not giving you any structure of phi x or anything like that. Yes. Absolutely, absolutely. It's pretty straightforward, right? I mean, think about it. You give me any phi x, yeah, it doesn't matter what you give me, give me this phi x or this phi x or this phi x or whatever, I mean, some kind of increasing function, yeah, you give me any phi x or phi norm of x, yeah. Once your problems begin, and I am talking about now V being below this, what do I want? V has to be below this guy, right, but your problems begin once you freeze the x, yeah, once you freeze the x you are frozen here. So for this guy you are frozen here, 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 wherever, I do not care where you are frozen, but my V, this guy is not just a function of states in this case, there is another another element that I can play with, it is time, right. So this picture is not very representative, whatever value of these guys you give me, your class k function is frozen. That is it, it is a constant, as good as a constant. You gave me a constant, it does not matter how big a constant you gave me, I will choose my t to be really large, because this has to hold for all t. The left hand side has t, right hand side has no t. So I will bump up my t as much as I want, because I can go all the way to infinity, right, and then this will fail. My V will actually you know, if this was for t equal to t1, I will make for this guy for v t2 same x or v t10 same x, right. I just bump up t and I will dominate. There is no way any class k function will stand, right. Why? Because the class k function by the nature of the definition is only a function of x. Once x is frozen, the class k function evaluates to a constant. However large this constant, I have time still to play with on the left hand side, and in this case it is an increasing function of time. So this is where your class L should somehow think about, you should think about. Whenever I have some increasing function of time here, some strictly increasing function of time which is in fact going to infinity, I have a problem. You cannot claim that it is class k, it is a, you cannot claim decrescence in this case, okay, because this will always dominate any class k function, no problem, okay. So absolutely correct. I am going to delete this, sorry, right, okay, is that clear? Okay, this is not decrescent, okay, that is what I have said, and this is fine, I mean it does not matter, I mean what I have said here. The basic point is right hand side only function of x, left hand side increasing function of time, even if x is constant, I am done, cannot, this domination is not possible, alright. Okay, again decrescence connected to uniform stability. Alright, suppose I flip this thing, suppose I flip the example, that is now it is not an increasing function of time but a decreasing function of time. Life is good. Why? Now it is definitely greater than equal to norm x square by 2 for all t, because as t has to be greater than equal to 0, negative t's are not allowed, okay. So I can't make this really large and all that, okay. So for non-negative t, this is of course dominating norm x square by 2, this is of course being dominated by norm x square by 2, right. So I am done, okay, decrescent. Now obviously it is not positive definite though, I hope you understand by the same argument. If you give me any class k function to compare with, I know that this is a decreasing function of time, I will keep bumping up time and I will go below your class k function, okay. So this can never dominate any class k function, therefore it is not positive definite, okay. So somehow one might get an impression that both seem mutually exclusive, right. If you have a positive definite function, you did not get decrescence, if you got decrescence, you did not get positive definiteness, okay. Seems like there is some mutual exclusivity here which would, but then that would mean that if you get stability you cannot get uniformity, if you got uniformity you cannot get stability, that seems a bit ridiculous, right. So are there functions which are both positive definite and decrescent, because that is what we need for uniform stability, right. We said that decrescence is connected to uniformity, positive definiteness connected to stability. So unless I have both positive definiteness and decrescence, I cannot claim uniform stability. So what are we saying? There is no uniformly stable systems in the universe. So can you tell me if there is a function which is both positive definite and decrescent? How do you think we can get a function which is both positive definite and decrescent? I gave you an example of positive definite, I gave you an example of decrescent, now I want both. Time bounded function. Yeah, little bit more I'll say it is to be bounded on both sides, okay. It is a function that is bounded, the time is corresponding to time bounded on both sides, which is why I had introduced this example earlier. 1 plus sine squared t by 2 x squared, norm x squared. So what do I know? It is greater than equal to norm x square by 2. I already proved it for the purpose of positive definiteness, right, because sine square is lower bounded by 1, but then this is also upper bounded by 2, right. So there is both a lower bound Greater than 0 lower bound, by the way, that is important. You can't have a equal to 0 lower bound or a less than 0 lower bound. It has to be a greater than 0 lower bound. So, the lower bound was 1, upper bound is 2. So, the lower bound is this guy, upper bound is this guy, yeah, both sides satisfied, okay, not so complicated actually, yeah, until you have the example seems complicated, but not so complicated, right. It is both decrescent and positive definite, has both the properties. Unfortunately, we do not have any shorthand for decrescence, we actually write it just like greater than 0, less than 0, unfortunately we do not have any shorthand here, you have to actually write that it is decrescent, okay. So, now this is a good function to have, this lets you sort of evaluate both properties, yeah, okay. If there was no such function, it would be very funny, okay. Okay. Obvious, just like we said that uniformity for time invariant systems is free, just like that if your V is purely a function of states, then again uniformity is sort of free, yeah, there is nothing to, no decrescence to evaluate, it is decrescent and it is positive definite because there is no time argument in this itself, okay. So, decrescence and positive definiteness, anyway sorry, decrescence is free, yeah. Alright. Finally, we have the property of semi-definiteness, which is a very nice and weak property, yeah. Again similar arguments, 0 at 0, scalar valued continuous, and it just has to be greater than 0 as a, greater than equal to 0 as a function, okay, for all time, for all x, non-negative, that is it. So, all the examples we considered, they were all semi-definite at least, yeah. T x1 square plus x2 square, obviously this is the in fact positive definite also, x1 square by 2, x1 square by 4, semi definite, okay, x1 plus x2 whole squared, semi definite, because as functions, yeah. So, this is also gives you a big distinction between semi definiteness and definiteness, okay. Semi definiteness is just a property of that function, it is like how you, when you are plotting these functions, how you look at it, it is above 0, below 0, that is it, okay. As a function it is positive or negative, it is just, so a non-negative valued function which is 0 at 0 is semi-definite, okay. But when you talk about positive definiteness and negative definiteness, there is certain definiteness, alright. You are basically looking at rather special properties, okay. These are not just basic properties, yeah. Again, why one might ask, why we do not like these semi-definite functions, okay. Look at this again, think about inverse of V, all our analysis when we look at proofs and so on and so forth, they rely on V inverse, okay. Now, if I talk about V inverse of 0, okay, in a positive definite function, when I say V inverse of 0, what comes to your mind? 0, 0 states. But if I look at a semi-definite function, V inverse of 0 is what? Straight line, all possible infinitely many states. Again, this guy, again the y axis, right? All possible infinitely many states come to mind. Ridiculous, right? I mean, the question is, what is it that even, I mean, you can't even like talk about an equilibrium in these scenarios, right? How do you even talk about equilibrium? If you, the V inverse 0 is not a single point, then it's, the V is irrelevant or useless for, as far as Lyapunov theorems are concerned. Not to say they are useless in every context, they are actually also methods which can let you conclude stability using just semi-definiteness type properties, but not of V, of V dot, okay. So, those are basically what are these LaSalle invariants and Barbalat's lemma and things like that. Those are methods that let you talk about global or asymptotic stability when V dot is only semi-definite, okay, not V. V being semi-definite, still tough, again still not impossible, you can do some analysis there, okay. Alright, any questions? So, We have not gone to the proof of, at least of the Lyapunov theorem. We are actually going to state them now. But when you look at the proof, all the proof for the Lyapunov theorems are based on V inverses, taking the inverse of the V and looking at what you get, which is why I made this picture, where I made this picture and said that, if you take V inverse of this set, you get exactly this set. So, this bounded set gives a bounded inverse, but here this bounded set does not give a bounded inverse. So, that kind of problems, okay. The proofs rely on inverse of these functions, okay. So, what is the setup for the Lyapunov theorems? Nonlinear system, function of time and state, time from t0 to infinity, usually t0 has to be greater than 0, greater than equal to 0, and states in a ball of radius r. Mapping to Rn is this function f with some initial condition. Without loss of generality, we assume that 0 is an isolated equilibrium, okay. F is assumed to be locally Lipschitz continuous. This is for existence of unique solutions. We already spoke about this in the first class itself. And finally, we define the notion of Lie derivatives, okay, or directional derivatives. Nothing complicated. What you think of as V dot, what comes naturally to you as the derivative of V is actually the directional derivative. Why we use this different notation and different sort of method of talking about it is because when you write a V, for example, I wrote some function V like this x1 square plus x2 square, alright, this is such a common function, alright. I can use this to analyze hundreds of dynamical systems, okay. Hundreds of dynamical systems could possibly be analyzed by the same V, okay. So, the V itself has no connection to any dynamical system. V is just a function of some states, not a function of, nothing to do with any dynamical system. But we want to study how V evolves along the solutions of a dynamical system, okay. So, we take its derivatives along the trajectories of a particular system, and when we identify this V with trajectories of a particular system, what you compute as V dot is just partial of V with respect to time plus partial of V with respect to states times ftx is the LFV, is the Lie derivative, okay, it is called the Lie derivative, okay, it is the directional derivative of V, okay. So, this is the notation, but as far as you are concerned, you are just computing V dot, okay, alright, great. If there is a nice C1 function V mapping time and states in a domain to real numbers such that for some r positive such that it is positive definite, this much assumption, the highlighted assumption, if you have this highlighted assumption to be satisfied, then this function V is already called a candidate Lyapunov function, okay, this is the terminology. It is a candidate Lyapunov function if it is a C1 function of time and states and positive definite, then it is a candidate Lyapunov function. Then in the sense of Lyapunov, if V dot is negative semi-definite, origin is stable. If V dot is negative semi-definite and V is decrescent, then origin is uniformly stable, okay. So, these are the first two Lyapunov theorem, very simple statements. I have written them in a very simple way. If you go to the textbook, of course, there is a little bit more buff in the statement itself, because it writes a lot of things and so on, writes the system and so on and so forth, but the basic statement is pretty simple. You take the V, evaluate the V dot, of course you verify that V is positive definite, otherwise it is not even a candidate Lyapunov function, right. So, that is clearly specified here, okay. If it is not this, then it is not a candidate Lyapunov function, you cannot use it for the Lyapunov theorem, okay. You can use it in other places, we will talk about those examples later on, but for Lyapunov stability theorems, no, this is essential, okay. And then we say that system is stable if the derivative of V, the way we defined it, is negative semi-definite. Only semi-definiteness required. And further, if V was also decrescent, then you have uniform stability. Yeah, you can already see the simplicity of this result. Once you have a V, evaluating stability is just super easy. Of course, it's not, remember, nothing is easy. Yeah, having such a V is also, it's something that you try to find. Yeah, just because you took a random candidate Lyapunov function V and V dot turned out to be not negative semi-definite, does not mean your system is not stable. It just means that you did not find a good enough V. Okay, so this is only sufficiency condition, as you can see, not necessary condition. Yeah, there is an existence necessary condition, but that will not help you find the Lyapunov function. Okay, so Lyapunov functions are constructed primarily by experience, previous literature, energy of the system gives you some motivation, but it's still a hunt. Okay, so this is one of the complaints most people have about nonlinear systems, but this is why I love nonlinear systems, because it's not just, you know, for everything I take X transpose Px and it works. No, it doesn't work. You have to put some effort into constructing this V, and more often than not it captures some fundamental property of the system. Okay, just like energy of the system captures a fundamental property of the system. Okay, so if you have a Lagrange system, then energy remains constant. So you know that V dot is, if you take energy as your V, then V dot is exactly 0. Therefore, it's a stable system. Lagrange systems are stable systems. Okay, so this kind of a simple conclusion can be obtained. Alright.